In section 8.6, we're going to talk about solving rational equations. I'm going to show you two methods. I'm going to show you the algebraic method. My algebraic method is a little bit different from the way the textbook does it. But I'm also going to show you how to do this on the graphing calculator. You've actually done this on the graphing calculator before, it's just that you're going to be typing in a lot more expressions and you have to watch your parentheses. A rational equation is going to be one that contains at least one rational expression. That means at least one of the fractions in the problem has to have a variable in the denominator, because if it doesn't, then it's not a rational equation. The way the algebraic method is going to work for this first problem is we're going to do the same thing we did in the last section. You know how we were adding things together and we needed common denominators? We want all of the fractions to have a common denominator, because if they all have the same common denominator, then the denominators become something called negligible. That means we don't need them anymore. So I want you to notice that the first denominator is x minus 3, the next one's x plus 3, but x squared minus 9, that's one of our special factors, x plus 3x minus 3. So how am I going to get all of these fractions to have the same common denominator? So the first fraction, if it had an x plus 3, then it would have the same denominator as this, because I want you to notice the other two fractions, one of them has an x plus 3, one of them has an x minus 3. That means this is the least common denominator. So the first fraction needs an x plus 3. The second fraction has an x plus 3, but it needs an x minus 3. And the third fraction doesn't need either because it's already got the least common denominator. So what happens now is these denominators basically go away. So you're left with the algebraic equation x plus 3 plus x minus 3 equals 2. And we're going to solve that equation. Well, we know how to solve that equation. We're going to distribute x squared plus 3x plus x squared minus 3x equals 2. We're going to combine like terms. 2x squared, 3x and negative 3x cancel, equals 2. I'm going to divide by 2, and I get x squared equals 1. And when I square root both sides, I get x is equal to plus or minus 1. Don't forget, when you take a square root, you're going to put the plus or minus sign there. Now, here's the question. Do both of these solutions work? Remember when we were doing radical equations, and if we did the problem algebraically, we had to go back and check our answer for something called extraneous solutions? Well, you kind of need to do the same thing here. Will either 1 or negative 1 make any of those three denominators equal to 0? Well, it doesn't take that long to figure out that the answer is no, because the only numbers that will make the denominator 0 are 3 and negative 3. So the solutions must be 1 and negative 1. To do this problem in the calculator, the best way to do it is to set the equation equal to 0. So not only did I set my equation equal to 0, but I also showed you what it looks like when I type it into y1 equals, because it's actually too long on the screen for me to show you the whole thing. So I did x over, and notice the parentheses, x minus 3, plus x over parentheses, oops, that should be x plus 3, sorry, minus 2 over x squared minus 9. Why is it minus 2 over x squared minus 9? Because what I did was I took that entire rational expression that was on the right-hand side of the equation, and I subtracted it from the left. And notice that I made y2 equals 0. The reason I did that is because if you want to use the intercept function, solutions are where the graph crosses the x-axis. However, what I did was I graphed it and then I zoomed in, so I want you to see that it hits at negative 1 and positive 1. The calculator does not give extraneous solutions, so both of these solutions must be correct. All right, let's do this again in problem B. In order to solve this algebraically, I want all three denominators to have the least common denominator. Let's factor this first denominator and see what I get. The two numbers that multiply to give you positive 2 but add to give you 3 are x plus 2 and x plus 1. We're going to give you relatively simple problems here, so I want you to notice that, look, all three denominators have x plus 2 and x plus 1, so what's the least common denominator? This one. So what I'm going to do, and leave this in factored form, is figure out what each fraction is missing. Well, the second fraction could use an x plus 1. And the third fraction could really use an x plus 2. Now that I've determined what the fractions have missing, so that they all have a common denominator, now the denominators go away. So now I'm left with just the numerators, and I'm going to simplify and solve that. So I have x minus 1, I need to distribute here, plus 2x squared plus 2x is equal to x squared, let's see, plus 2 minus 1 is plus 1x minus 2. I skipped steps in my process of distributing, FOIL, because at this point in time, you should be able to do it relatively quickly. All right, so in order to solve this problem, I'm going to need to get it equal to 0. So I'm going to subtract x squared from both sides. I'm going to combine some like terms here to make this nicer. When I subtract x squared from both sides, 2x squared minus x squared is 1x squared. X plus 2x is 3x. I haven't done anything with the x minus 2 on the right yet, so how about I subtract x? I'm left with 2x. And I still have a minus 2, so I'm going to add 2. And I'm left with x squared plus 2x plus 1 equals 0. This, in factored form, is x plus 1, x plus 1. So x equals negative 1 is the solution. Now remember I said when you go and solve this algebraically, you have to go back to the original problem and check for extraneous solutions. So in the original problem that I typed in black, will a solution of negative 1 make any of those denominators equal to 0? Uh-oh. It's going to, isn't it? It's actually going to make both of those 0. Well, if it makes any of the denominators 0, then that solution doesn't exist. So it turns out that not only is this extraneous, but there must be no solution to this problem. Now, just as a side note, if you are having trouble with factoring, you can also go back to the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And it would have given you the same answer. Here at the top of the screen, I showed you how I plugged it into my calculator. Notice all the things in parentheses. Anytime you have an expression, a number plus a variable, minus a number times a variable, you need to put in parentheses. As a matter of fact, when in doubt, if you're not sure if you should use parentheses or not, just use them. So I didn't show you the graph, and the reason I didn't show you the graph is because it appeared as if it actually hit the graph at negative 1. But if you go to the table, notice that at negative 1, y1 says error. That means the graph does not exist there. That's why this is no solution. I purposefully skipped problem 2. I'm going to come back to that in the next video. For now, I'll skip to problem 3 because they do their graphing to find solutions just slightly different than I do mine. And I'm going to show you both ways because some of you have actually already discovered the way the book does it. So when you go put this in your calculator, Again, if you aren't sure if you should use parentheses, here's what you should do. You could do this. Again, this is a little bit different from the way the book types it in. Maybe that's just because they are using a different version of the calculator. I don't know. But the way the calculator does it is it puts the left-hand side of the equation in y1 equals, and it puts the right-hand side in y2 equals, and then it finds where those two graphs intersect. So on my calculator screen, it looks like this, which is actually the same as it looks in the book packet. What you'll notice is that that line y equals 1, that's kind of going right there. I'm sorry, I drew that poorly. It's like an asymptote to two parts of the curve, but clearly it looks like they intersect right there. Well, if you want to find the point of intersection, just use your second trace 5, enter, enter, enter. And it's going to tell you that the intersection is at 0, 1. But when we find the intersection, we only care about one number, and that's x. So it says that the solution is 0. And if you go back up to the top here, you'll notice 0 does not make any of the denominators equal to 0. However, if you do it the other way that I had shown you how to do it, which was to set the equation equal to 0, and then you make y2 equal to 0. So in order to make the equation equal to 0, you had to subtract 1 from the other side. You would notice the graph, it has a very similar shape, but there's something a little different about it. Again, we still want to know where the graph intersects the x-axis. That's what this means. Where does it hit the x-axis? Well, it looks like it hits the x-axis at the origin, and if you do second trace 5, enter, 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 it's still going to tell you that x equals 0. So in this section, please, determine how you want to solve it. You want to try to do it algebraically. That's not a bad idea. But also feel free to utilize the calculator and see if you can find the solutions that way. Either by setting y1 equal to the left-hand side and y2 equal to the right-hand side, or by setting the equation equal to 0, making y2 equal to 0, and finding where the graph intersects the x-axis.